Hello, dear students. Today we will start another topic that is heart rate variability, and we will refer to as HRV. So, heart rate variability, it refers to the physiological phenomena of variation in the time interval between the heartbeats. It is measured by the variation in the beat to beat alterations interval. It can also be referred as cycle length variability or RR variability or heart period variability. HRV, that is heart rate variability, can be determined by measuring each occurrence of a specific component of the ECG waveform. The most common point of the cardiac cycle used when measuring heart period is the peak of R wave. This is due to the fact that the R wave appears as a sharp positive peak followed by a negative deflection. The peak of the R wave is normally greater in amplitude than all other peaks in the ECG, making it easily distinguishable. We are also calling sometimes this RR interval as NN interval when we are considering normal rhythm, and it is also known as interbeat interval, that is IBI. Now we'll see how this HRV is generated. The intrinsic heart rate generated by the sinoatrial node in the absence of any neural or hormonal influence is about 100 to 120 beats per minute. However, in a healthy individual, resting heart rate would never be that high. In a healthy individual, mainly we are talking about the adult, the heart rate is ranging between 60 and 90 beats per minute. This shows the net effect of the parasympathetic nerves, which slows the heart rate, and the sympathetic nerves, which accelerate it. So we'll see the effect of autonomous nervous system on intrinsic heart rate. So as we know that autonomous nervous system is divided into two, that is parasympathetic or vagal system and the sympathetic system. So parasympathetic is mainly when the body is at calm state, or we can say at rest, and sympathetic is a kind of fight and flight response. Parasympathetic inhibits heart's functioning, whereas the sympathetic stimulates heart's functioning. Parasympathetic, it acts only after sympathetic stimulation has taken place, and high sympathetic stimulation is normally equal to high heart rate or stroke volume. In parasympathetic, the heart instantaneously responds to parasympathetic stimulation, whereas in sympathetic response, heart's response to sympathetic stimulation that is normally equal to 5 seconds. Now, we'll see the effect of this autonomous nervous system on HR in terms of this figure. This figure illustrates the variability in heart rate due to the autonomic nervous system, which acts in balance through neural, mechanical, and other cardiovascular parameters in their optimal stages and to react optimally to changing external or internal conditions. So you can see we have different sources to produce this variability in heart rate, respiration, blood pressure, thermoregulation, or other influences like stress. So they will influence the parasympathetic as well as the sympathetic case, and then we can have feedback depending upon whether it is a parasympathetic case or a sympathetic case, whether it will be a positive kind of feedback or a negative kind of feedback, and they will produce change in instantaneous heart rate, or we can say heart rate variability. Now, what are the different sources which produce heart rate variability, as we have seen some of the sources in last diagram? So let's see now this. We have two. One is extrinsic. In that we have activities, mental stress, physical stress, smoking, and then we have intrinsic periodic rhythms, that is respiratory sinus arrhythmia, baroreceptor reflex regulation, thermoregulation, neuroendocrine secretion, circadian rhythms, and other unknown rhythms. So they will basically produce the heart rate variability. So errors in the location of the instantaneous heartbeat will result in errors in the calculation of the heart rate variability. Now, how we measure the heart rate variability? So we have a number of methods like time domain method measures, frequency domain methods, or we can also say spectral analysis, and we have non-linear methods. In this, we will mainly concentrate on time domain and frequency domain measures. In this lecture, we will concentrate on time domain measures, and in next lecture, we will see about frequency domain measures or the spectral analysis of heart rate variability. So we can see in this diagram also, the process involves RR interval correction, because as we mentioned, if it does not produce this RR interval correctly, definitely it will produce some error in the measurement of heart rate variability. So RR interval correction, then we have NN interval sequence, and from this we have time domain HRV features, and then we interpret and resample this to produce frequency domain HRV features. Now let's start discussing about the time domain measures. So time domain methods calculate a number of variables that describe either the heart rate at any time or determine the intervals between successive normal complexes. As they are applied directly to the RR interval series, they are the simplest ones to compute. In a continuous ECG record, each QRS complex is detected, and so-called normal to normal, that is, this is RR, or we can say NN interval, that is all intervals between the adjacent QRS complexes resulting from sinus node depolarization or the instantaneous heart rate is determined. They are further divided into two. One is statistical methods and other is geometrical methods. So the geometrical measures are derived from the RR interval histogram and are relatively insensitive to the analytical quality of the RR series. The current geometric methods are not very appropriate to evaluate short-term recordings. So we'll start discussing now about statistical methods. In this, some are simple time domain measures which we normally sometimes generally we go for checkup and we do these kind of measures, that is mean RR interval, which is for example 100 millisecond. Then we have mean heart rate, that is 60,000 millisecond by 1000 millisecond, and it comes out to be 60 BPM. Then minimum RR interval, for example, it can be 700 millisecond. maximum RR interval that can be 1200 millisecond, and the difference between the RR minimum and the RR maximum, that is minimum RR interval and maximum RR interval is 1200 minus 700, that is coming out to be 500 millisecond. So these are some approximations, and these are different simple time domain measures that can be done to measure heart rate variability. Now, how we define this mean RR interval in millisecond and mean heart rate in beats per minute, they are defined by the equation. So you can see this will give RR minimum, that is a mean of RR interval. So this can be RR1, RR2, different measures of this RR divided by number of measurements we are taking. So it is average of RR interval, and mean heart rate is again average of heart rates. So here N is the total number of all RR intervals. Now we have some complex time domain measures. So in this we have number of parameters, so we'll see one by one. So the first parameter in this is standard deviation of NN intervals, and generally we say it as SDNN. This is measured in millisecond. It is calculated over a 24-hour period, thus it encompasses both short-term high-frequency variations as well as the lowest frequency components. It reflects all the cyclic components responsible for variability in the period of recording. Therefore, it represents total variability. The actual values of SDNN depend on the length of recording. The longer recording is, the higher will be the SDNN values, and it is calculated as you can see in this formula: square root 1 by n summation I equal to 1 to n RRI. This is one any kind of interval because I is running from 1 to n, minus the mean RR. So it is measured in millisecond. Then we have another parameter which is standard deviation of the average NN intervals, and it is represented again in millisecond, and it is also referred as SDANN. It is calculated over short periods, usually 5 minutes. It provides the measure of standard deviation of the average of NN intervals in all 5-minute segments of entire recording. It is therefore a measure of changes in heart rate due to cycles longer than 5 minutes. So SDANN, it is calculated as square root 1 by n summation again I running from 1 to n RR, this should be RRI minus RR average whole square. So that is mean, basically standard deviation we are calculating, so it is square. So here where this n is the total number of 5-minute sections RR intervals in selected segment. So why we kept 5 here specifically, that is the mean of average RR interval in 5-minute section. So we kept 5 here, and RR is the mean of all means of RR intervals in all 5-minute sections. This should be double bar. So that is mean of the mean. That's why we are keeping here double bar. Now next parameter is root mean square of successive differences, that is RMSSD. Again it will be measured in millisecond, and it is a square root of the mean of the squares of the successive differences between adjacent RR or NN intervals, and this measure estimate high frequency variations in heart rate in short term RR recordings, and it is calculated as you can see in this formula: RMSST is square root 1 by n minus 1 summation I is again it is running from 1 to n minus 1 in this, and RRI plus 1 minus RRI whole square. So this is RMSST calculation. Now we have another parameter, that is standard deviation of successive differences, that is SDSD. Again, it will be measured in millisecond, and it is the standard deviation of the successive differences between adjacent NN intervals, and it is given as SDSD, as you can see, equal to square root 1 by n minus 1 summation I is running from 1 to n minus 1, then mode of RRI minus RRI plus 1 minus mean of RR difference whole square, and here n is again the total number of RR intervals, and RR difference bar is described as you can see in this formula. So mod of RR1 minus RR2, similarly mod of plus means it will add further terms, RR2 minus RR3, like this it will go up to RRn minus 1 mod of RRn minus 1 minus RRn divided by n minus 1. It can also be represented this in compact form. Now we have another parameter, that is SDNN index, that will again it will be measured in millisecond. It is the mean of standard deviation of all RR interval for 5-minute segments of entire recording, that is for approximately 24 hours. It measures the variability due to cycles which are shorter than 5 minutes. And it is given as you can see average of all standard deviation in intervals, where n is the total number of 5-minute section of RR interval in the selected segment. Then we have another parameters, that is NN50. This is the number of pairs of successive NNs that differ by more than 50 milliseconds, and it is used for classification of the segment which is longer or at least 5 minutes. So as you can see in this, it is given by summation I is equal to 1 to n mod of RRI plus 1 minus RRI, and that will compare with 50 millisecond. Then we have PNN50, that is proportion of NN50 divided by total number of NNs. So it is NN50 divided by N into 100. Then we have NN20. It is number of pairs of successive NNs that differ by more than 20 milliseconds. Again we have PNN20, that is proportion of NN20 divided by total number of NNs. And we have another, that is estimated bridge cycle. So the range, that is maximum to minus minimum within a moving window of a given time duration within the study period. So that is estimated bridge cycle. The windows can move in a self-overlapping way or be strictly distinct, that is sequential windows. This EBC is often provided in data acquisition scenarios where heart rate variability feedback in real time is a primary goal. Then we have some of the geometrical methods. One parameter in that is HRV triangular index. Total number of all NN intervals divided by the height of the histogram of all NN intervals measured on a discrete scale. So that is total number of NN intervals divided by Y, that is the highest peak we can say in the histogram. Thus, if the discrete approximation of the measure is used with NN interval measurement on a scale different to the most frequent sampling of 128 Hz, then the size of bins will be 7.8125 millisecond, that is 1 by 128 second. You can see in this diagram also. So this is the peak. You can see here this Y. That is the peak in the histogram, that can be continuous, that can be discrete. Then we have another parameter, that is triangular interpolation of an interval, that is TINN. Baseline width of the minimum square difference, triangular interpolation of the highest peak of the histogram of all NN intervals, that is M minus N. You can see in the last figure, this is M and N. So that parameter will be M minus N. Then we have differential index. Difference between the widths of the histogram of differences between adjacent NN intervals measured at selected heights. We have another parameter, that is logarithmic index. So coefficient phi of the negative exponential curve, it is given as k e raised to power minus 5t, which is the best approximation of the histogram of absolute differences between adjacent NN intervals. Now, what are the different applications of this heart rate variability? So, heart rate variability, a measure of autonomic function, can predict survival outcomes. Heart rate measured as beat to beat interval is not constant and it varies in time. That is, HRV has been investigated in several diseases. So the diseases mainly includes diabetes, cardiovascular diseases, myocardial infarction. We also use it to detect sometimes the cancer. So this was all in this lecture. In next lecture, we will discuss about the heart rate variability, mainly the frequency domain measures. So for now, for this we can refer the book DC Reddy, that is Biomedical Signal Processing Principles and Techniques. So for now, thank you so much.